All right. In the last video, I showed you how to take a map that you made with Skynet of a large part of the sky, turn it into an image using radio cartographer, and then we put it in this tool, the radio source finder. And I'm going to show you how to use this tool in the next video. But before doing so, we should pause and talk about the different types of sources that you're going to be looking for. We're going to be using an astronomical service called Simbad. Basically, once we set this up, we'll click on various bright spots in the image. It will take us to Simbad, and it will list every source in that part of the sky. And since this map is so big, and these sources being single dish radio map sources are so blurry, there are going to be a lot of sources. No matter what source you click on here, there are going to be a lot of sources in that part of the sky. Stars, X-ray emitters, gamma ray emitters, all sorts of things that are not necessarily relevant. And we have to search through that haystack and find the needle that we're looking for. So what are those needles? What are we looking for? What can we expect to find in our radio map? And we'll talk more about this in Module 4B, but just in case we're not doing 4B this year, I want to give you a quick overview of the three major continuum emission mechanisms. We've already talked a little bit about line emission. When you have a process that emits just at a single frequency. Like in the optical, the H alpha emission line, the O3 emission line, and the S2 emission line. Those are common in the optical. In the radio, it's the H1, 21 centimeter emission line. That's line emission. But we have different types of continuum emission as well. And there's one you're already familiar with, and that's thermal blackbody radiation. We learned about that back in Module 1B and 1C. Here's the thermal spectrum, the Planck spectrum, the blackbody spectrum. You get this when whatever you're looking at, if it's an opaque gas. Opaque means the light doesn't get through. So in the gas, light is being generated. By light, again, I can mean radio waves, infrared, gamma rays, any type of light. It's being generated by different processes. Might be line emission, it might be other things. And if the gas was transparent, that would just stream right out and we would see whatever was generated. But if the gas is opaque, the light doesn't make it out. It bumps into stuff, gets scattered all over the place. Sometimes it's absorbed and re-emitted over and over again. And this changes the spectrum of the radiation, and what comes out of an opaque gas is the blackbody spectrum, the Planck spectrum, the thermal spectrum. And we've seen this before. You have two regimes. You have the Rayleigh-Jeans tail, and the radio is down there. And the equation that we used before, that's for the Rayleigh-Jeans limit. Then at high frequencies, it turns over. You have this exponential cutoff. Because of that, take something like us. We are blackbody emitters, about room temperature, about 300 Kelvin. And so because of this exponential cutoff, we do not glow at visible wavelengths. We are glowing in the infrared and also down in the radio. Okay. Now, we've already learned that the moon is a thermal emitter, and we did have another example. Here's the sun. Here's a picture of the sun made with a radio interferometer, the VLA, the Very Large Array in New Mexico. And you have two types of emission. You have the sunspots, and that is not thermal. Come back to that in a second. But then you have the emission across the surface. It's fainter, and that is the emission of 5,800 Kelvin blackbody. That's the temperature of the surface of the sun. Now, stars, they're thermal emitters, but the sun is the only star that we're really going to be able to see with our radio telescope. All the other stars in the sky, they're just too far away, too faint to see their thermal emission. So really, in your maps, you're not going to be seeing thermal sources, but it is the first and very important type of continuum emitter. We see it in the optical with stars all the time. Now, we're not going to see it in the radio, except for those cases I just mentioned in the solar system. So what will we see in the radio? And there are two continuum emission mechanisms to keep in mind. The first is Bremsstrahlung. Pop over here and show you that. Bremsstrahlung is braking radiation. You get it when you're looking at a hot, dense, and transparent. Unlike the last case, which was opaque gas, this is a transparent gas. So hot, dense, and transparent. Hot is important because the gas needs to be ionized. If it's hot, the electrons separate from the protons. Most of the gas is hydrogen. So once it ionizes, you have a plasma, protons and electrons whizzing by each other. It needs to be dense, so you have a lot of interactions. If it's low density, they're not going to run by each other very often, not very many close encounters. But if it's a high enough density, they will encounter each other quite often. And when they do, they deflect around each other. And with the deflection, you get a deceleration of the electron. Now, when charges decelerate, they emit light. And again, it can be any type of light on the electromagnetic spectrum, including radio. So you get a continuum of radiation. And what does this look like? Kind of like this. At very low frequencies, that gas actually is opaque. And so you get the Rayleigh-Jeans tail, same as before. But at higher frequencies, it is transparent. And in an opaque gas, the light has a hard time getting out. It keeps scattering and changing its nature. In a transparent gas, it just streams out. So the spectrum that's created from this at high frequencies streams out, and you see it looks like a black body curve. This is called thermal Bremsstrahlung. It looks like a black body curve, but it doesn't have that exponential cutoff. It's pretty flat out here. Okay, so that's Bremsstrahlung emission. Now, when we're in Sinbad, looking through our lists of sources, what types of sources are we looking for Bremsstrahlung emitters? Put up the sheet of notes here. So here's thermal, opaque gas, moon in the solar surface, and you. But here's Bremsstrahlung, hot, dense, transparent gas, and the kinds of indicators you're looking for, primarily H2. H1 means neutral gas. The electron is still coupled with the proton as an atom. H2 is ionized hydrogen gas, so they're separate. It's a hydrogen plasma, a proton-electron plasma, so a hydrogen ionization region. And you get these around hot stars, O stars, B stars. They spit out a lot of ultraviolet ionizing radiation, ionizing the gas around them. So H2 is what you're looking for in the Sinbad lists, though sometimes it could be listed as SFR, star-forming region, or dark nebula. There may be some other ones as well. These are the ones I've encountered the most so far. Okay, that's Bremsstrahlung radiation. The third continuum process, and the second that we'll see a lot in our radio maps, is synchrotron. We already learned a little bit about that. The teams that studied Jupiter realized it was not thermal emission, it was synchrotron emission. So you get synchrotron emission when you have energized electrons in a magnetic field. the electrons will spiral around the field lines. And that's like in Bremsstrahlung emission, where you deflect the charges, or in thermal emission, where everything is vibrating and shaking. Whenever you're moving charge, you're emitting light. And again, it can be across the electromagnetic spectrum. So you have a magnetic field, you have electrons, particularly if they're energized, have a lot of energy to give. As they spiral around, they will emit that energy, giving you a spectrum of radiation, a continuum spectrum. And it looks very different from the black body. Bremsstrahlung looked a lot like thermal, not at the high end, but at the low frequency end. Synchrotron is very different. Its spectrum is inverted. It's very bright at the radio frequencies and gets dimmer. And so a lot of the stuff that we see, particularly very far away, like from other galaxies, that's synchrotron emission. Now, I'll mention the sources of that emission in just a second. I should note that since the black body curve drops suddenly at high frequencies, we sometimes also are synchrotron dominated up in the X-rays and the gamma rays. So you can study and receive synchrotron radiation at both ends, though often in the middle thermal dominates. Okay, so what kinds of sources? Jupiter, as we found out before, we calculated its black body temperature. It was way too high and concluded it was synchrotron emission from Jupiter's magnetic field. Also, these spots on the sun, it's due to magnetic fields popping through the surface. It's hot, it's a plasma. Those electrons get in those field lines, spiral around, and so they're dark spots in the optical, but very bright spots in the radio, brighter than the solar surface. So the solar emission is dominated by synchrotron, except at solar minimum when there are no sunspots, then it's just the thermal that you see. But what else? Two classes of objects in particular that we're going to be looking for: supernova remnants and supermassive black holes at the cores of other galaxies, and our own galaxy, perhaps. Let's start with the supernova remnants. So when we get to the unit on star death coming up, we'll continue to walk through the story of stellar evolution. The end of Module 2, we left off at the horizontal branch, but there's more that happens after that. And the most massive stars, they end in a supernova explosion, where the star expels its outer layers in the form of a shock wave. And that shock wave works its way out into space, running into gas, and it accelerates the electrons. Sometimes the electrons pass the shock front a couple times, and they get accelerated and energized. And that's one of our ingredients for synchrotron. The electrons need to be energized. Then you have to have magnetic fields. And all stars have magnetic fields. But when a star explodes, those magnetic fields get carried out in the ejecta, in the expanding shell. They're all tangled out here in the outskirts, right where you're accelerating the electrons. And so they'll then spiral around those field lines, decelerating and emitting their radiation. So supernova remnants glow in the radio. And here are just a couple examples. This is Cas A. It went off in about 1680, so it's very young, very, very bright. One of the brightest things in the radio sky, but you can barely see it in the optical because it's behind so much dust. Another example is Taurus A, the Crab Nebula. This went off in 1054 and was seen by people back then and recorded. And it emits at all different wavelengths for all sorts of reasons, but emits in the radio due to synchrotron. And there's a pulsar, excuse me, a pulsar in there, and we'll study that a little bit later as well. Okay, then you have supermassive black holes. Now, we think there's one of these at the center of every galaxy. There's no reason why there wouldn't be. galaxies are full of stars, stars die, and stuff that starts out about 25, 30 solar masses ends up as a black hole. It's pretty rare, but in a whole galaxy, you'll end up with black holes all over the place. And one of them will be the lucky one that's fairly close to the center. And so it gets fed periodically because whenever a galaxy is disturbed, come back to that in a second, when it's disturbed, gas falls down the gravitational well to the center. And the black hole just gobbles it up and gets more massive. But it's a process. There are a couple steps. So the gas falls down and it doesn't stream directly into the black hole. It usually will be coming in on some tangent. So it ends up settling into a disk. We call this an accretion disk around the black hole. And that material starts to work its way down through friction towards the black hole. And it's hot. It's very hot there. So hot that it will ionize the gas. And you have free charges. And when you have charges moving in loops, those are circuits, and they generate magnetic fields. And in this case, the magnetic fields will be oriented along the rotation axis of the accretion disk. Now, most of the stuff in the accretion disk will work its way into the black hole due to friction. Its orbit will decay, it will get closer and closer, and eventually fall into the black hole. And that's how these black holes turn into supermassive black holes. If you happen to be the lucky black hole sitting near the center of the galaxy, as the gas streams down, you get fed, you grow, and become supermassive. Our galaxy's central black hole is probably about 4 million times the mass of our sun. And that's on the low side of the spectrum. Some galaxies have central black holes that are billions of times the mass of our sun. And these act as very strong gravitational engines powering the radio emission that we see. Now, how do we get that radio emission? Well, not all of that material working its way through the accretion disk ends up in the black hole. Some of it will get caught up in these magnetic fields and shot out along the rotation axis at high speed, sometimes a few tens of percent the speed of light. So you have energized material, energized electrons, they're in magnetic fields, they will spiral around the field lines, and you will have synchrotron radiation. Now, the only part of this story I haven't explained is why is the gas falling down to the center? What is feeding these black holes? And in a galaxy such as ours, we're fairly normal, fairly stable. There's not much gas flowing down at any given time. Some leading to slow, steady growth of the black hole. But black holes really get fed when the galaxy has an interaction or a collision with other galaxies. If a galaxy passes too close to another galaxy, they gravitationally disturb each other, and the gas gets destabilized and falls down the gravitational well, feeding the central black hole. Or if a galaxy absorbs a small orbiting galaxy, that can disrupt the gas in the same way. Or if you have a major collision between two big galaxies, and that's what's going on here. Let me blow this figure up. This is Cygnus A. This is our primary calibrator of the radio sky. The gold is a Hubble Space Telescope picture, I believe, and can't see it very well, but you have two spiral galaxies just slamming into each other. And the radio is depicted in red. This is a picture made with the Very Large Array in New Mexico. And so here, that spot at the center, that's the central black hole, the very base of the jet. But that material is ejected many times the size of the galaxies. It's really spit very far out there. It's piling up material as it goes, and eventually it piles up more than it can push forward, and so it starts to expand sideways and poofs out, looking like this giant Q-tip. And you get all this radio emission out there. Now, some things you get more radio emission from the concentrated center, some you get it more from the extended radio jets. So, what do all these things look like in Sinbad when you're in there trying to identify what source is related to your detected radio emission? The list is quite long. You're trying to go through it, trying to figure out what's relevant, what's not. Here are a few things to look for. Under the category of synchrotron radiation, you have SNR, supernova remnant, and radio emission from jets that are coming from accretion disks around supermassive black holes, from other galaxies. They can have a variety of names. If the emission is more centrally concentrated near the black hole, we call those AGN, active galactic nuclei, or QSO, quasars, which is kind of a more extreme version. And these can change their brightness from year to year. Now, on larger scales, filling out these jets, that kind of brightness is more steady. You may see SY1, SY2, Seyfert galaxies. This is usually due to a minor collision with a spiral. Or you may see RG with a little r. Those are radio galaxies. Those are major collisions, creating very big, strong radio jets, kind of like we see here. If you see a capital RG, that's a red giant. We're not looking for that. So little RG. Actually, when you're in Sinbad, anything denoted with an asterisk, that's just a star. You can ignore those. Some things you may see depicted RAD, just for radio source. And that just means they really don't know what it is. It's just something emitting radio waves, probably an H2 region or a supernova remnant or a supermassive black hole, but we don't know which. Okay, that's it for this video.